Our next speaker is Jack Feser. He's going to talk about inductive program synthesis guided by observational program similarity.
Great, thanks. So this is joint work with my old advisor, Armando Solar-Lezama, and Işıl Dillig. Before I start telling you about the things that are new, I want to do a brief recap of synthesis with bottom-up search. So here we have a little arithmetic DSL specified by a grammar E, and we'd like to find a function f that satisfies some input-output examples. The simplest thing we can do is to just start enumerating programs, starting from small programs, and building larger and larger programs by composing the programs that we've already found together using the operators in our DSL. This works just fine. The downside is, of course, that the space grows very quickly. And so in practice, we often want to apply some kind of optimization to this kind of synthesis. In particular, it's very common to use an optimization called observational equivalence reduction. And observational equivalence reduction takes advantage of the observation that if we have programs P and P prime, and they do the same thing on some vector of inputs I, then it's always safe to treat P and P prime as if they were equivalent during synthesis, even though in practice they are probably not actually truly equivalent. So the way this works, it is a slight modification of our previous approach. We build our programs from the bottom up in the same way, but in addition, we keep track of the behavior of those programs on our inputs I. So we form a characterization vector, and we use those vectors to cluster programs together into equivalence classes. And we only retain one program per equivalence class. So when we go back to our example and we run this, what we see is a very nice reduction in the size of our search space. We find our answers more quickly. Everyone is happy. The downside is that this doesn't work in every domain, and we ran into a couple of domains where this really very much doesn't work. So to give you an example, consider the inverse constructive solid geometry domain, or inverse CSG. So the goal here is to start with a picture like we have on the left, and to write a program that generates that picture by composing primitive shapes like circles or rectangles, using Boolean operations like plus and minus, and other operators like in our DSL we have a kind of repetition construct. So if we think about this DSL, we immediately run into a fairly difficult problem when it comes to the use of observational equivalence. And that problem is that this DSL produces an enormous number of very, very similar but not exactly equivalent programs. So here we have all the different ways that you can take the center out of a circle. And if we just shift or scale or move that center slightly, we get a program that is distinct from the perspective of observational equivalence, but that is very much not equivalent to the program, to the other programs in this set. So small program changes result in small behavior changes, but those behavior changes mean that these programs are not equivalent. So observational equivalence really falls down in this domain. But as a human, our insight is really that any one of these programs should be fine. We could replace one with another, and we would end up with a small perturbation in our output, but we could probably repair that perturbation after the fact. So we extend this insight. We basically take this insight and we say, okay, well, what if we used similarity as a kind of replacement for equivalence? We say that programs P and P prime are observationally similar if the distance between their behavior on some inputs is less than some epsilon. So here, this distance d, this is going to be specific to the domain that we're working in. So what happens if we do this? What happens if we replace equivalence with similarity? We define similarity classes that are analogous to equivalence classes, and we keep a single representative for each class. We, of course, get a reduction in the size of the search space. We are clustering programs together. But we also get error. Essentially, what we've done is we've said, well, our representative program is going to be the circle with a square taken out, and it's similar to everything in its class, but it's not the same as the circle with the circle taken out, so we can only generate this close but incorrect program. So if this is going to be useful, we have to come up with some way to mitigate this error. And what we have found is that in practice, this error is actually very mitigatable. And what we can do is we can take a program that is close but wrong, and we can attempt to repair it. And in our work, we use a rewrite system. Essentially, we apply rewrite rules. We guide the application of those rewrite rules using our distance function. So we perform a kind of hill climbing search, applying the rule that moves our erroneous program closest to the goal program. And we repeat this until we find a correct program or we fail. So at this point, we essentially have a synthesis algorithm. We perform a bottom-up search, very analogous to the kind of bottom-up search that we would perform with classic equivalence reduction. And then when we have finished building our search space, this is, if you're familiar with FTA-based synthesis, this is a very similar data structure, but instead of representing the programs that satisfy some examples, we represent a space of programs that almost satisfy those examples. We then extract programs from that search space, and we apply rewrite rules to attempt to repair them. And we repeat this process until we solve our problem. So the bottom-up search looks almost exactly the same as it does for standard synthesis with equivalence reduction. We repeat an expansion step where we generate new programs by composing programs we have found. And then we perform a clustering step. This is analogous to equivalence reduction, but in our case, we're doing clustering. We're building clusters of bounded radius using our distance functions. We then perform a ranking step to attempt to select the clusters that we believe will be most useful in solving the overall problem. We retain those top K clusters, and we continue building our space. In our implementation, we build this space up to a bound, and then we begin extracting programs from that space, picking programs that are accepted by states in our finite tree automaton that are closest to our goal. We extract programs, and we incrementally repair those programs by applying rewrite rules guided by our distance function and the goal behavior. So in practice, this algorithm is pleasantly general. We can parameterize it over our domain-specific language, which we give by a grammar G and an evaluation function E. We also have to provide a distance function delta that tells us something about the similarities between program behaviors. And we have to provide rewriting rules R that we use for repair. We chose to use rewrite rules because they're a little bit more flexible than something like gradient descent, although gradient descent I think would likely work here. But rewrite rules allow us to do both continuous changes like scaling or moving or resizing, and also non-continuous changes like this translation from circles to squares, which turns out to be important for the CAD domain. Okay, so we implemented this algorithm and we parameterized it for 3 fairly diverse application domains. Inverse CSG, which we've talked about. We also looked at a tower building domain, which is a kind of AI task where you're controlling a little robot arm that moves left and right across a playing field, and it drops blocks to build towers. And then finally, we looked at a regular expression building domain. So let's look at some results. So for inverse CSG, you might be able to tell, this is the domain that we designed the system around. So the performance is quite good. This was really our motivating domain. Here we look at 25 randomly generated benchmarks, 22 handwritten benchmarks, and we compare against 3 baselines. First, we compare against an instantiation of Sketch. This was used successfully for inverse CSG in prior work, but it's very brittle. So changing the DSL in any way causes that technique to collapse. And so when we looked at it, what we found is that it really was not able to perform very well because the DSL was modified in a way that caused the Sketch algorithm to really change its performance characteristics. We also looked at bottom-up enumeration, which is the blue line, and we looked at an instantiation of an abstraction-guided search. So we built an abstraction that we used for clustering in the abstraction-guided sense. In all of these cases, we found that the baselines were quite bad at inverse CSG, and this is part of the motivation for looking at this problem. Looking at the regular expression domain, we see that the baselines are quite a bit stronger, but we are still outperforming them. Here we look at the prior state-of-the-art. It's a tool called Regel. It's a top-down synthesizer, and it uses some very clever solver-based pruning techniques. We also looked at bottom-up enumeration and abstraction-guided search. And what we see here is that bottom-up enumeration, the blue line, FTA, is actually quite strong. But where it starts to fail is where it starts to hit its memory limit. So what we see is that our algorithm is equivalent in performance to bottom-up search in this domain, but it's less memory hungry. It needs less space to represent its programs. So it's a little bit better suited for maybe more memory constrained domains. And so that's where we see that performance improvement. And then finally, we looked at a tower building domain. This was drawn from some work in the more AI side. It came from the Dreamcoder paper. And here we compare against a neural method from Nye et al. We also compare against bottom-up enumeration. We actually don't compare against abstraction-guided synthesis here, and there's details in the paper. This actually turns out to be a fairly difficult domain to instantiate that technique in. And we think that this maybe indicates that it's a little bit easier to instantiate this similarity-guided stuff in some domains that are harder for techniques like abstractions. Here we don't see the performance achieving what we can do with a neural method, but I think we're fairly competitive, and we have the pleasant benefit of not requiring a training step. Okay, so the last result I'd like to share with you is a little ablation study that gives you a sense about what parts of the algorithm are most important. So here we looked at our algorithm, the full thing, it's on the top, and then removing various pieces. So this is for the inverse CSG domain. And what we can see is that if you basically make the repair step random, if you randomly explore repairs, the whole thing collapses. The repair step is very, very important. If you turn off ranking, again, the whole thing collapses. So picking clusters that are close to the goal program is also very important. Clustering and the technique that we use to extract programs from the search space are both important, but they are less important than ranking and repair. And that this distance function that we choose, we used a custom distance function for this domain. It's a small variation on the Jacquard distance. It's explained in detail in the paper. We wondered how much that domain insight mattered. And so we turned that off, and we found that it does matter, but pleasantly, it doesn't matter as much as the other parts of the algorithm. So you can get away with relatively simple distance functions. They don't have to be tweaked perfectly for the domain, but tweaking them more does improve performance. Okay, so to conclude, we've presented an algorithm that uses the similarity between programs to cluster them as we search. And we've shown that this can actually significantly improve performance on some of these interesting sort of continuous-like domains, like inverse CSG, and that we can recover from the error that we introduce with that clustering by doing a kind of hill-climbing search. We think that this algorithm could be applied in a number of other domains, and I'd be very interested to see people use it in other places. I'd also love to see, there's a lot of interesting future work here, and one thing I'm interested in looking at is trying to take some of the expert knowledge out by replacing the distance functions with some kind of learned distance. The challenge here is that these distance functions are extremely performance sensitive, so any kind of learning would have to be quite performant. But that would be interesting to see in the future. All right, so thanks so much for your attention. I'd be more than happy to take questions.
Thank you very much for the very interesting talk. So I think your approach depends on the property of the domain, that the similarity between the output of the program indicate the similarity of the program themselves. Otherwise, you cannot repair them. So
yes.
I'm wondering to what extent this property holds. You have already shown at least in 3 domains the property hold. I'm wondering if there's a general characterization to what extent it holds.
I think characterizing this kind of property in general would be very interesting, but I think any sort of characterization that's sort of parameterized over the space of domains is, you're asking a really wicked question here. We talk about this in the paper, so we give some formal requirements to get completeness. One thing I didn't say is that this algorithm is not complete unless you satisfy our requirements, and our requirements are very strong. So we have some sense of what you need to do to make this complete. Most domains I don't think satisfy it. I think the takeaway for me here is that you can get much better performance than some of these complete techniques. So if you want an answer, try this, but it may not give you as many guarantees as you would like. Does that address your question?
Yeah, I think so.
Okay, thanks.
Thank you. Yeah.
Oh, hi, I'm Jose from University of Edinburgh. You mentioned that to build, let's say, the initial space, you still use like enumerative a search, so you like the initial space and then the clustering thing.
So the clustering is interleaved. Basically, if you know how a bottom-up search works, you're expanding and then collapsing into equivalence classes. Replace that collapsing step with a clustering algorithm. We use something custom because we want clusters of bounded radius. So like k-means doesn't work.
Yep.
Sorry, I kind of cut you off.
So yeah. So my question is, when you just pick up like one representative program per cluster, so you make sure that you don't waste a lot of time exploring programs that are similar itself. My question is exactly when do you like decide given you're in a cluster and you did not find your answer with your repairs, how do you decide which cluster you will go next? Like, is it also based on the distance function on the?
We look at the clusters in order of their distance to the goal, and we spend a fixed. Basically, it's a hyperparameter that tells us how much time to spend on each cluster.
Oh, okay.
Yeah.
All right. Thank you.
Yeah.
For distance function, what is the distance function for the other two domains that we have in the benchmark? So for X and
so for regex here was it's example driven. So we're looking at the actually the match sets, so the places in the output string that match, and we're looking for how many examples we get, and for the examples that we don't get, whether or not we even match the part that we're supposed to match, even if we match other places. I would have to check the paper for the exact details on that one. On the tower building domain, we take advantage of the insight that in this domain, it's actually quite easy to translate the towers left and right. That requires a very small program change. So basically, it depends on where the arm starts. So the distance function is sort of translation invariant, but it pays much more attention to the shape of the tower. So it normalizes and then does a distance comparison. So the distance function is really encoding quite a bit of domain knowledge here.
Okay.
Does that help?
Yeah, that helps.
Okay.
Hey, okay. So the question I have is, when you want to learn a function f, typically you think about how many examples I have to show the system so that it can learn f, right? So did you also notice that as you go on showing more and more examples, even without the repair process, you're converging to the right answer? Did you observe this phenomenon in your experiments?
We didn't try giving it more examples in kind of an incremental way.
Okay.
For CAD, the examples are not independent, so you really have to give them all. For regex, you could give the examples independently, and for towers, the example, there's only one example. It's the single tower. So there's not really an incremental process here.
Okay, got it. Thanks.
Yes.